promise. This is the Halloween episode, so all of our examples are going to be creepy. Although before this, Matt told me my spooky examples are really just dark. So we'll see. All right, so we covered the tenets of simple and conditional probability last time. But now let's talk about what we call counting methods. And why do we call them counting methods? Well, if you ever ask, how many ways can a hockey team be able to
I think we lost Aubrey for a second.
Well, echoes aside, we're going to learn about permutations and combinations, which are the two major divisions of counting techniques. All right. So a quick note, something we forgot to cover yesterday. If you ever see, what's the probability of at most X number of things occurring? That includes everything beneath that as well. So, for example, what's the probability that there are at most 3 cases of Ebola in a given country? So this includes probability of 0, probability of 1, 2, and 3. Anyway, if you're working through a probability class, you will probably see an at most or at least question versus exactly 3 cases. All right. So we have to get to Toronto. And for whatever reason, I'm not willing to just drive the entire way to Toronto. Maybe I'm not willing to pay for Airbnbs, whatever. So there are going to be 2 legs to the trip. The first leg, we have 3 options to get to Philadelphia. So we have train, POV, which is a personally owned vehicle, and a Greyhound bus. 3 options for the first leg. On the second leg, we go from Philly to Toronto, and there are no trains suddenly, so we either hitchhike or we take a plane. And how many different ways can we get there? So there I listed out all of the possible, in this case it's a permutation because order matters. So there are 6 options, but when you get to many legs of many trips or where there are many options, it's not really feasible to just list out all of the possible combinations. So we use the handy dandy formula. You're going to multiply how many options there are for every step of the journey by each other. So in this case, there are 3 steps in there are 3 options in the first leg and 2 options in the second leg. Our number of options is 3 times 2. I used m times n here. You could use any variables you like. So that's a basic counting method. And this could go on for a very long time. If there are 17 legs of the trip, we could multiply all the way down the line. So do you know why we multiply them? Recall back on Monday when we multiply probabilities of things.
They're all independent activities.
Yeah, they're independent activities. So let's think independently. I want the probability of me taking train and hitchhiking, personal vehicle, and then taking the plane. So you should be seeing little ands in your speech as you talk about this. All right, so that's counting methods basics. So what if we have 11 stuffed animals, 11 zombies, 11 pieces of cake that are different, and we want to just set them up in a line? Every time we use one, we're taking it out of the sampling pool and we can't reuse it. So if we have 11 stuffed animals and we're lining them up, there are 11 options for the first step. The other 10 animals are still hanging around. So then there are 10 animals for the second step, and 9 for the third, 8 for the fourth, 7 for the fifth, etc. And we can write that as 11 factorial. So there are a lot of different ways you can line up 11 stuffed animals. And you can't reuse them. We'll see later situations which you can have replacement, and that'll be slightly different. So keeping in mind what you currently know about counting, I would like for everybody to use Annotate. It's going to be about half of you working on problem 1 and half of you working on problem 2. So this is our little warm-up set. So come on and write your initials in the vicinity of 1 and 2. Brendan, will you tell us how and why you solved number 1 as you did?
So we assume that you only pick one type of chocolate, one type of blood type for the filling, and then one option for the dried insects. And so you just end up taking 3 times 4 times 7, 3 for the chocolate, 4 for the filling, and 7 for the insects. I don't really have a great formal explanation for it other than that makes sense in my head.
Yep. Well, makes sense to me too. All right, Beth, how many license plates do we have to sift through to find our serial killer?
A lot. 7 times 10 to the 52nd power number of license plates. And how I got that was on the license plate, we know the first 2 characters, U and Z, but we don't know the 3rd letter character. And there are 26 options for letter characters. And if you use one, that means you aren't using another one at the same time. So I set it up to be a 26 factorial just to get that one space figured out. And then the last 4 figures are going to be numbers. There are 10 possible numbers if you include 0. And so those 4 spaces, again, if you're using any one number, you can actually use it again in a different space. So that's why the times 10 factorial, times 10 factorial, times 10 factorial, times 10 factorial. And when you multiply all of that together, you get a very large number.
So I would say for now, until we show the combinations and permutations with replacement, we're gonna leave the factorials. I would solve that 26 times 10 times 10 times 10 times 10.
Right. So if you can't reuse a letter or a number, then it would be that.
So you don't need the factorial there yet, unless you know what a denominator would be, and that's kind of like peeking ahead. You could solve this a different way once we've looked at other types of notation, but there would be a denominator to go along with this. But to keep it simple, you would take out the factorials and you would solve it the same way. So it'd be 26 times 10 times 10 times 10 times 10. Because that's how many options there are at each stage for each digit. Yeah, here we go. So I don't see any furrowed brows, but I see some 1,000-yard stares. How are you guys doing with this? All right, I got a little bit of feedback. Okay, cool. Everything. All right, so when we talk about permutations, we are assuming that we are selecting a certain number of them and that their order matters. So you can do this with or without replacement. So if you want to repeatedly select an object and you can use the object multiple times, it's just like the digits in that license plate, it's the number of digits available to you times itself, however many spots you need to fill. So n to the r power. N is your number of objects you're choosing from, and r is the number of slots. And if you can't reuse objects here on out called without replacement, then it's just n factorial because you're subtracting 1 each time. So what if you only want to select a certain number of objects from within? For example, I want to cast a bunch of actors for my roles, but I only have 3 roles. So R, in this case, is the number of objects that you want to select, and N is your total pool to choose from. So this is described as n permute r, but it's n factorial over n minus r factorial. So let's see it. Let's see the other alternative, if order doesn't matter. So here are the equations. R and n are still exactly what they were before. Repetitions are not allowed, it's n choose r. And Python and R both know what n choose r are. You can also do n choose r in Google, and that actually has a built-in calculator. But if repetitions are allowed, you're going to follow r plus n minus 1 choose r. Don't worry, I give you guys these equations later, and we're going to look at some word problems to see how you might interpret these. But I see some people happily scribbling. Oh. All right, give me a thumbs up when you have everything you written down. All right. All right, Beth, you almost ready?
Almost. And done.
All right, so in this first example, let's see, we have different types of pedophores with different types of filling and frosting. Here's some of the different types. And if crispy, I think this is like Krispy Kreme maybe, I'm not sure. If they offer 8 varieties of pedophores and we want a box of 12, no repeats, how many different boxes could we make? So
that's with repeats.
With repeats, oh. I'll let you take this one over.
Oh, I'm realizing now as I see the slides on the side, there's an example slide between permutations and combinations that somehow didn't pop up when I did it.
Oh, I'm gonna go ahead and pause share and you can share on your screen.
Okay. Are you pausing share?
I did. Oh, there we go.
All right, cool. I really hope that's the last time my computer crashes. It's a work supply laptop, you guys.
It made the scary sound again.
Oh no. All right. So a permutation example where order matters and we don't have replacements. So we're trying to put on a zombie version of the Book of Mormon. 120 zombies audition, and how many ways could she cast the play? I don't know if you guys have seen the Book of Mormon, but literally 7 guys do the voices for all of the characters. And there are a lot of characters. But so this equation is n factorial divided by n minus r factorial, n permute r, if you would. And so here it's 120 factorial divided by 120 minus 7 factorial. So there are a ton of ways that 120 people could be cast into these roles. And order does matter because you can't substitute Alder Price out for any other character. He is who he is, and people can't just change roles like that. So keep this in mind for when order matters. Then crispy, I named this hypothetical place crispy because I figured the little bug legs would crunch as you bit into the chocolate. But Krispy Kreme is spelt with a K because it's Southern and that's how they roll, I guess. But yeah, these would be interesting donuts. So using the formula for repetitions are allowed because you can reuse the same petit four multiple times, we're going to use this top one. So 50,388 different boxes. All right, this should be 36, not 56. All right, a zombie hockey team. Why not? So at a given time, there are 6 guys on the ice. But for now, zombies aren't very used to playing hockey, so we're just picking the guys who can ice skate pretty reasonably. So we don't know the positions yet. We are casting for 20 players, and there are no replacements. So in this case, it's 36, which are the number of guys coming out for tryouts, choose 20. And that's the number of zombies you get. And the reason that it's different from number 1 is that we can't reuse zombies, but we can reuse the same flavor of petit four.
Hey, Aubrey. The first one, like I don't understand the formula. Maybe you covered it before. Like, why is m plus r minus 1? Where does the minus 1 comes? I know the formula is like that, but I just want to understand. Why is not choose 20, like choose 12 from 20?
Or choose, well, because if you were writing out all of the final like ratios of probabilities, then the last one would be, there would be an extra, oh gosh, proofs. So basically how you get here is you make it like permutations where order matters, and then you do a little bit of algebra to make it as though the order doesn't matter. So you add back in the probability on the top as if the order doesn't matter. And then when we're talking about choosing with repeats allowed, I don't know if there's some big theoretical reason for where the minus 1 comes in, but just like when you're making it work, you don't have as much wiggle room in the top as you would when you don't have repeats. I don't know, it just kind of condenses like that. There's not any big theory that goes with it.
Okay.
But yeah, I can look for a proof after this class and then send it to you if you're looking for that.
Yeah, that would be really helpful.
Okay. Yeah, I can look for that. Actually, I can look for it now while Matt covers how to do this in Python.
All right, so we're going to jump into a notebook now. It's the Permutations and Combinations notebook in the repo. So I'll give you a second or two to pull that up. And just give me a thumbs up when you got the notebook up and running. All right, is everyone good? Juliet? Yep, okay. All right, so we're gonna look at a few problems here and kind of do them in Python. So if we look at this first one, a witch is brewing up a wicked concoction and is trying to decide on ingredients. She has 6 different varieties of bat wings and 4 varieties of eyes of newt. If she can only add 3 total ingredients to her brew, how many possible choices of ingredients can she make if she needs to include at least 1 eye of newt in that combination? So when you first look at this, you might think it's kind of simple. You know, she could have 1 eye, and then that's a bat wing. That's also a bat wing. So you could have 1 eye and 2 bat wings, or you could have 2 eyes and 1 bat wing, or you could have 3 eyes total. But there are 6 different varieties of bat wings and 4 varieties of eyes. So there's actually more possibilities than that, because each of these can be one of many. So in order to figure this out, we can kind of look at our 3 different possible scenarios here in terms of the number of eyes versus the number of wings. So for this first example, for the eyes at least, that is, let's see. So there's 4 possible eyes, and we're going to choose 1. And then for the bats, it's 6 possible ones, choose 2. So then we'll add this to these next ones. So for the second, there's 4 possible eyes, we choose 2. And then 6 possible bat wings, and we choose 1. And then for this last one, there's 4 possible eyes, and we choose 3. So if we add this together, we should get the total number of combinations. So to do this in Python actually doesn't have a built-in NCR function, so we can kind of make our own here. So to do that, we need to import math, and then we'll just call it n choose r, and we'll pass in a value of n and r. And then this is just a little trick. You can assign a function to a variable just to shorten it. So the math library has a factorial, and this will just let us call it by putting f instead of math.factorial. And then we just use the formula, so return f of n. And now we want to do the double division sign here. It's kind of a complicated reason, but basically if we get into really large numbers, if you do regular division, it converts the numbers to floats, and Python doesn't like dividing by really large float numbers. So this is integer division, and you have to use it for that reason. So divided by r factorial divided by n minus r factorial. So that should give us the function we need. So now for this first part, we can do ncr, and we can pass in 4 and 1 times ncr, pass in 6 and 2, plus ncr 4 and 2 times ncr 6 and 1, plus ncr 4 and 3. And if we run that, we get 100 possible combinations. So I'll go ahead and clear this. Let's see. All right. So for the next one, a group of 4 ghouls and 5 zombies attempt to line up to take turns feasting on a victim. If 2 zombies stand close to each other, they will attempt to feast on themselves. So with this in mind, how many possible ways can we line up these 5 zombies and 4 ghouls so that no 2 zombies are standing next to each other, basically? So the way to think about this is kind of to draw it out. So if we have 4 ghouls, 5 zombies, how can we line them up so that no zombies are next to each other? Well, we have to kind of alternate. So we can do zombie, ghoul, zombie, ghoul, zombie, ghoul, zombie, ghoul, 1, 2, 3, 4, and zombie. So this is basically the only way we can lay it out. And then to calculate the possible ways this can be arranged, we can break it down. So the zombies, they have to stay in those spots, but this could be zombie 1, zombie 2, zombie 3, and they could all switch around. So for the zombies, at least, that's going to be 5 factorial, because there's 5 different zombies, 5 different places they can be. And then for the ghouls, it's basically the same thing. There's 4 of them. So it's going to be 5 factorial times 4 factorial. And we can go ahead and use the math.factorial function here.
Hey, Matt, but ghouls can be in front of zombie as well, right?
Yep, but to line them up, you couldn't do it any other way, because then 2 zombies would be next to each other.
Oh, okay, got it.
Like if you try moving a ghoul to the front,
Right,
then
right,
the
right.
2 zombies will be next to each other.
Got it.
So then it's just math factorial of 5 times math.factorial of 4, and 2,888 possible ways. So I'll give you a second to copy that down. Does that make sense to everyone? Thumbs up if yes.
I have a question on the previous one. Sorry.
Okay, that's fine.
So does it say that? So how about like C10(3) minus C6(3)? So I use subtraction. So in total we have 10 ingredients, right? And the event space will be C10 choose 3, and I delete all the all the possible outcomes if we only have wings. So that's C6 choose 3. So if I use C10(3) minus C6(3), I think that's the correct answer.
So that would be the correct answer if all of the bat wings were the same and all the eyes of newt were the same, but it says they're different varieties. So like there could be a vampire bat wing, another kind of species of bat wing. So there's basically 6 different kinds of wings and 4 different kinds of eyes of newt. So that makes it more complicated because then all those ones can be interchanged. Does that make sense?
No. So even though it's different varieties, it doesn't say like what variety they need, right?
Right, so you could have, so these would be the wings, you know. There's 5 different kinds, and then the eyes, there's 4 different kinds.
Oh, there are 6 wings.
Oh, 6 wings, okay. So there's all the possible ones. And now, okay, so for the first set, I can pick 1 eye and 2 wings. So there's 4 different eyes to choose from for that first eye. And then for the 2 wings, there's 6 different to choose from. So I could do E1, B1, B2, but then I could also do E1, B1, B3.
Yeah.
So you can see how there's going to be a lot more combinations then, since these are distinct.
My result is 600. Yours is 100. So.
So what did you say yours was?
Like C10(3).
10(3).
Minus C6(3).
Oh, that's actually the same.
Wait, is my formula wrong? Oh yeah, sorry about that. Yeah, my formula is wrong. So actually it works.
Yeah, I'm trying to think why that works. Aubrey, do you have an idea just off the top of your head?
Well, this how we solve it in high school. Like you just basically use the total event space and you minus all the possible outcomes that you would have no eye of newt.
Yeah, I guess that does make sense because here you're just subtracting the ones where you have all bat wings, like you said.
Right.
Okay, so yeah. So apparently there's more than one way to solve that.
Cool.
Is everyone else good with that? If we move forward? Yep, okay. All right, so we did the zombie one. Now we'll go to a variation of a very classic combination problem dealing with handshakes. So at the annual ghost party, all the guests greet each other by shaking hands. If there are 1,000 ghosts at the party and all shake hands with each other once, how many handshakes will occur? So this seems like it'd be hard. So whenever you're faced with a hard problem, you can try making it simple first. So if we have a room of, let me get the right thing here. So if we have a room of 2 ghosts, we'll just call them A and B. Then the only handshake that can take place is A and B, and that's 1. If we have 3 ghosts, then we could have A and B, A and C, B and C. So that's 3. Yep. And then for 4, we could have A and B, A and C, A and D. Then we could have B and C, B and D. And then we could have C and D. So that's 1, 2, 3, 4, 5, 6. So can we tell any pattern from this? So at 2, we get 1, at 3, we get 3, and at 4, we get 6. Well, if you keep doing this out, you may notice that eventually it becomes n times n minus 1 divided by 2.
Right.
So if we plug in 2, 2 times 2 minus 1, that's 2 divided by 2 is 1. If we plug in 3, 3 times 2 is 6 divided by 2 is 3. So that works there. So then to solve, in this case, we would just do 1,000 times 999 divided by 2. And that would give us the answer. So let me go ahead and run this here. So 1,000 times 999 divided by 2. And we get almost 500,000. But so another way we could think to do this is to just do 1,000, choose 2. Because we have 1,000 ghosts and we need to pick all the different pairs of 2. And so what if we run and choose, or 1,000 choose 2 with our function above? So 1,002, we get the same answer. So those are actually the same. Let me see here. So if you think about it, the formula for combinations is n factorial over r factorial times n minus r factorial. So this should be equal to n minus 1 over 2 when r is equal to 2. And to prove that that's the case, we can write it out this way. So 2 factorial is just 2 times n minus 2 factorial. And now I'm actually going to write it over here because I have more space, so hopefully you can follow that. But if we wrote out n factorial, it would be n times n minus 1 times n minus 2, so on and so forth. And down here we have 2. And if we write out n minus 2 factorial, that's n minus 2 times n minus 3, so on and so forth. So you can see that these parts actually cancel out. And we're left with n times n minus 1 over 2. And that's why they're equivalent. Does everyone follow that? Cool.
If you didn't follow it, do you feel like you would still be able to apply the equation and get to the results?
Some people are saying yes. All right, let's go down to the last one here.
Before we move on, I actually have a question.
Sure.
So is it wise to look for patterns like that whenever we're answering these types of word problems?
If you don't have any other ideas where to start, it can help. start off with small numbers, see if there's some sort of pattern. Kind of just depends. And then, I mean, once you've done enough of these, you'll notice like patterns between the problems. But whenever you see like a large number, that kind of makes things more complicated. So you can just try throwing smaller numbers in first.
Okay.
All right, so for the last one here, you're attending 3 Halloween parties and need a different costume for each one. You need to make a list of all the possible costume assortments you could have. So I've included a CSV file of just different types of Halloween monsters. So these will be like our ideas for the costume. So if you run that, it'll print out this pretty long list of different monsters. We can check the length of it here just to see how many there are. So 226. So if we wanted to figure out how many different costumes we could have, we could just do 226 choose 3, and we get this really giant number. But you'll notice the question asks, make a list of all the possible costumes. So thankfully, Python does have a way to do this. They have a library called itertools. And from that, we can import combinations. And then with the combinations, we can just do combinations, monsters, and we can pick 3. And if we run that, it'll take a second here. Let's see. Let's see, X for X in, oh, I had brackets instead of, there we go. So that'll just give us a combinations object, but then to get a list from it, we have to do a list. So it's just X for X in that combinations object. If we run that, then we can see we get all the possible combinations here. It's an incredibly long list. And you'll notice that if we increase the number of choices here, so now we're going to 4 different Halloween parties, it's taking even longer to run. And if you were to increase it to 5 or more, it would basically take like a really long time. So it's nice that they have this combinations tool here, but you have to kind of be careful because it can really take up a lot of memory and get really big really fast.
Are you frozen or am I frozen, Matt?
I think he's frozen because I'm here with you, Aubrey.
Okay. Well,
I think trying to do that list crashed his laptop.
Yep, that kind of proves his point.
Oh no. Well, so I can't share while he's still sharing, even though he's not here actually sharing. But I will say, just describing briefly. Okay, there we go. So if you're talking combinations without replacement, n choose r is the same as n factorial divided by n minus r factorial. When you're choosing from, how many ways can we put 20 people into 7 roles? And then, because order doesn't matter, we're multiplying that to kind of remove the effect of ordering that permutations had. And we're multiplying that by r factorial. And then it becomes n factorial divided by r factorial times n minus r factorial.
So that froze my computer, actually, running that last combination part. I think also the study group is just haunted.
I have never died this many times in a study group. So when we're talking about combinations with replacements, we need to add a little bit extra back in to add the extra probability that comes in because you're not removing an option every time. So if this one is n factorial divided by r factorial times n minus r factorial, then the fact that we can have duplicates ends up adding a little bit more to the denominator. So the -1 is adding a little bit of extra wiggle room for having a duplicate. So r plus n minus 1 factorial, or sorry, choose r is the same as r plus n minus 1 factorial divided by r factorial times n minus 1 factorial. And then if you were to write out those factorials, having this extra one, you would have 1 occur twice. So like every factorial ends with 1, and you have an additional 1 on the bottom that you don't have on the top. So when you reduce it, you have the n minus 1 factorial in the numerator, but not in the denominator. This was requested, you guys, so I just want to make sure that we have gotten what you need.
No, that makes sense.
Yeah, when we get to parameters and statistics, there's going to be a recurring trend of n minus 1 is like the degrees of freedom, providing hypothetical wiggle room for inference on the population. But for now, n minus 1 is just because the 1 in a factorial is included twice on the bottom, but only once on the top. All right, cool. So we're going to get rid of that whiteboard. So other than that crashing, did you have anything else you wanted to cover on that, Matt?
I think that was it. I'm not sure where I cut out. I think I was saying as you increase the number of combinations, the computational load really goes up, and it might take a long time, as you could clearly see.
Okay.
Oh, and also there's the permutation function in that library too, and combination without replacement, and a couple other things. So it's worth looking into.
Okay, cool. My Chrome crashed the last time. I lost my my PowerPoint thing, so I'm looking for it now. Oh goodness. This has been just a horrible day for technology, you guys. Okay. Let's see. So we've done our combination, our Python examples, and then finally here we are with a second round of practice problems. And to be a nice lady, I have included some equations here for you to use. So just like before, claim the problems you want to work on, and then we'll take 5 minutes. If you guys are feeling zesty, we can stay around for some poker examples after that. Matt, have you gotten any pictures of us in our costumes tonight?
I have not. If you want to do like a gallery view and take one. Okay. Also, I didn't realize that on the mobile Zoom app, you can still do annotate. Probably be a little difficult, but.
All right, I don't think I can do gallery view while I'm sharing the screen. Oh, we should stop recording.